In this video, we're going to talk about Unit 5, Objective 5, which is improper integrals. What an improper integral is, as far as AP is going to be concerned, you're really only going to see it one way, and that's the integral from some constant a to infinity of some function f of x dx. So generally, this is going to be some function that is going to be decreasing. So if you think about a graph that looks like this, so as you get closer and closer to infinity with that graph, we're going to get closer and closer and closer to the x-axis, so close that essentially, so if we go from, say, a, essentially as we get farther and farther out here, the area under the curve is going to be 0. So we're actually going to be able to get an answer as we go out to infinity. There's a little bit of verbiage that we're going to need before we talk about how to do this. We're going to say that an improper integral will converge if we have an answer. So if we find our integral and we come up with a numeric answer, we're going to say that it converges to that answer. Or we're going to say it's going to diverge if we don't get an answer. And part of what we're going to consider no answer would be infinity. So if we think about a function that looks like this, as we go farther and farther out to infinity, the area under the curve is getting more and more and more and more. It's getting bigger and bigger. So we're never going to actually end up adding 0 to our area. We're going to continue adding bigger and bigger numbers. So we're going to diverge. Our area would be infinite. Now, how we're going to find the improper integral is we're going to rewrite our integral and say from a to b of f of x dx. And then we're going to take the limit of that integral, not as x, but as b approaches infinity. And we're going to evaluate the limit there. So that's how we're going to get around taking an integral that goes to infinity. We're going to turn the infinity into a b, and then take the limit as b goes to infinity. So let's look at an example. We can say, what is the integral from 0 to infinity of 2 over x squared plus 4x plus 3 with respect to x? So the first thing we need to think about is, let's turn that infinity into a b. So I guess we shouldn't do an equal sign. Let's put a little arrow. We're going to turn this into a b. So 2 over x squared plus 4x plus 3. Now we got to think about, how do we take that integral? So a plain u substitution is not going to work, because u would be x squared plus 4x plus 3, which means du would be 2x plus 4. It's not a product, so we don't want to think about our differentiation by parts. So this is actually a partial fraction decomposition problem. So this is where we would have to factor out our bottom, break the fraction down into two separate fractions. So in the interest of time, I'm going to leave that up to you. So you can pause the video now if you feel like doing it, or you can just continue watching. So go ahead and pause it if you want to work. Alright, if you got it, we should end up at this, the integral from 0 to b of 1 over x plus 1 with respect to x, minus the integral from 0 to b of 1 over x plus 3 with respect to x. So if you don't know how to do that, go back, watch the video on partial fraction decompositions. Now we need to take the integrals of each of these things. We would use a u. The u's would be x plus 1 and x plus 3 respectively. Du for each of them would just be dx. So we can think about the integral of these things being our capital F of x being the natural log of the absolute value of x plus 1, evaluated from 0 to b, and minus capital F of x being the natural log of the absolute value of x plus 3, evaluated from 0 to b. So that would give us natural log of b plus 1. Now we don't need the absolute values anymore because we know that b is greater than 0. Minus natural log of 0 plus 1 is just 1. Minus, we'll put in parentheses, natural log of b plus 3. Minus natural log of 0 plus 3 is 0, so we're left with natural log of 3. Close all of those parentheses. So we're going to get natural log of b plus 1. Natural log of 1 is 0, minus natural log of b plus 3. And then minus negative will be plus natural log of 3. Since our first two terms have a b in them, we can combine those two terms and make it the natural log of b plus 1 divided by b plus 3 plus the natural log of 3. So that would be our integral in terms of 0 to b. But remember, our original problem said we need to go to infinity. So we need to now take the limit as b goes to infinity of natural log of b plus 1 over b plus 3 plus the natural log of 3. So if we think about plugging infinity into our problem, infinity plus 1 is still infinity. Infinity plus 3 is still infinity. So the limit of that first piece is infinity over infinity, which means we can use L'Hopital's rule. Right? Infinity over infinity is an indeterminate form. It's not going to be just 0 over 0. So the limit as b goes to infinity of the natural log of, take the derivative of the top, the derivative of b is 1, derivative of 1 is 0, derivative of b is 1, derivative of 3 is 0. And this other piece, we didn't have an indeterminate form, so we don't want to think about taking its derivative. Only use L'Hopital's rule on the indeterminate form spot. So now we try to plug b in again. There's nowhere to plug a b in, so we just have to evaluate the natural logs that we're looking at. 1 divided by 1 is 1, natural log of 1 is 0, so we're left with just the natural log of 3. So if you were to graph 2 over x squared plus 4x plus 3 from 0 to infinity and find all of the area under the curve, it would turn out to be an area of natural log of 3. So that'll do it for this video. We'll see you in the next one.